We're going to look for the general solutions of these multiple angle trig functions, starting with this first one. I noticed that I've got that multiple angle of 2 theta, but I'm going to start this the same way I start any other trig equation, and that's to isolate my trig function. I've got this 2 out in front here, so I want to divide everybody by that 2, getting that sine squared isolated first. So I end up with the sine squared of 2 theta is equal to 1 over 2. Next, I want to take a square root, so I can undo that power 2. So square root, and I end up with the sine of 2 theta is equal to, this could have been positive or negative, so plus or minus the square root of 1 over the square root of 2, which will be 1 over the square root of 2. Now, if you rationalize this by multiplying it by a radical 2 over 2, you're going to end up with the other form that you might recognize, and that's plus or minus radical 2 over 2. So either of these 2 forms should get you to a common angle. Now we are looking for a sine, which means that we are looking for a y coordinate. Let's take a look at the unit circle. I'm just going to go ahead and sketch where I've got the sine equal to 1 over radical 2, either positive or negative. These are going to be my pi fourths angles. So I've got one here, I've got one here, here, and here. So the angles that I've got are pi fourths. This is in 1 rotation of my unit circle, 3 pi fourths, 5 pi fourths, and 7 pi fourths. But when I say the angle that I'm working with is 2 theta. So I have that 2 theta is equal to any of these 4, but remember I wanted that general solution, so I want infinitely many. Instead of writing all 4 of these out, I'm going to recognize this great pattern. Each of these are separated by 90 degrees or a pi halves. So if I start with pi fourths and add multiples of pi halves, I'm going to get to all of my solutions, but I can also subtract those multiples as well. So that 2 theta is going to equal pi fourths plus multiples of pi halves. I'm going to write that as pi halves n, and n is going to be our counting numbers, so 0, plus or minus 1, plus or minus 2, and so on. But I really wanted theta instead. So I'm going to divide everybody by 2 to isolate that theta. Now, what does this give me? I end up canceling the 2's, and I've isolated now theta. So this is going to be my final general solution. I'm going to go ahead and do the math over here off to the side. So that pi fourths over 2 is the same as pi fourths times 1 over 2. Pi fourths times 1 over 2 is pi eighths, plus, now I've got that pi halves n, so pi halves n divided by 2, which is times a 1 over 2. That becomes pi fourths times n. So pi fourths times n, and we've got our general solution. Next up is this one, and I noticed that I've got these multiple angles of theta divided by 2. Well, I want to isolate this, but because I have a couple of terms in this expression, I'm actually going to end up factoring out this common tan theta divided by 2. So as I factor that tan theta divided by 2, I'm really dividing it off of both of these terms, so tan theta divided by 2, and I'm going to factor that out in front of parentheses. So we get a tan theta over 2, and then inside I'm going to put these in square brackets so it's a little easier to see where I've been. I'm going to do that first division. Tan divided by tan is 1, anything divided by itself. So I get a 1 here, and then I've got that minus 2 And I'm going to cancel those tan theta over 2's, and I'm left with that sine theta over 2. So I've got sine theta over 2 is equal to 0. Now, this is a product, and in order to get a product equal to 0, I need either the first factor or the second factor to equal 0. My two factors are these. So I've got a tan theta divided by 2 equal to 0, or I'm going to go ahead and put a line there, or 1 minus 2 sine theta divided by 2 equal to 0. I'm going to solve these two cases starting with that tangent. Now I know that tangent is y over x, so I want my tangent to equal 0. The only way to get y over x to equal 0 is if y was equal to 0. On that unit circle, y is equal to 0 over here at 0 radians and over here at pi radians. So I know that I've got these two angles within one rotation, but I want to go ahead and write out my general solution, and I notice a really nice relationship between those two. I can start at 0 and add multiples of pi, so plus pi plus 2 pi plus 3 pi, and then subtracting those as well. So for our angle, and remember that angle is theta divided by 2, we have found that theta divided by 2 is equal to 0 plus multiples of pi. So I can just call that multiples of pi, so pi times n. Now I want to multiply by that 2 because I really am solving here for theta. So I'm going to multiply both sides by 2. Let me move this up just a little bit, and I get part of our solution. I can cancel those 2's, and theta is equal to, I'm going to put n on the end, so I get 2 pi n. This is part of our solution. Let's look at our other case that came from that second factor. Now in that other case, I have a little bit of solving to do. I'm going to bring that 1 to the other side by subtracting that 1. So I get negative 2 sine theta divided by 2 is equal to negative 1. I'm going to divide both sides by that negative 2, by negative 2, by negative 2, and I get that sine of theta divided by 2 is equal to positive 1 over 2. Those sine values are my y values. So I want to know where on the circle are my y values of 1 over 2. Well, hopefully you recognize this as our 30, 60, 90 triangle. This is my smaller side of 1/2, which is opposite the angle pi 6. So I can come up with that value either here at pi 6, but my sine or my y's are also positive there in quadrant 2. I'm almost there to 6 pi 6. So the second one is going to be at 5 pi 6. But remember, this is my angle value theta divided by 2. So I can say that theta divided by 2, so theta divided by 2 is equal to, I really don't have a nice relationship here. So I need to write this out as a two-part solution. So I can take my pi 6 and add multiples of 2 pi. So this is going to be 2 pi n. And I can do the same thing with the angle in the other quadrant. So that would be 5 pi 6 plus multiples of 2 pi n. But I'm not solving for theta divided by 2. I want theta. So I'm going to go through and multiply the left side by 2 and the right side, both of the forms of our solution, by 2. So I'm just going to sneak a times 2 in here for both parts of our solution. Let's rewrite that 2 pi n so it's also part of our solution set. So I've got 2 pi n, and then I'm going to take this part, and that's going to give me 2 pi over 6. 2 over 6 is a 3. So I get pi thirds plus 4 pi n. And then that last part right here, I can again cancel the 2 and the 6, and I get a 3. So this is going to be 5 pi thirds plus 4 pi n for that, in all of its glory, for that general solution. In this one, I notice that I've got 3 terms, and that first term is squared. So I'm going to think of this as a trinomial, and I'm going to factor it into 2 binomials. So I'm going to have 2 values here times 2 values here equals 0. As I'm going through these, I want to start by making, let me get rid of some of this here. I want to start by making the first 2 positions, so that would be here and here. Those are going to multiply to be my sine squared 4 theta. So I'm going to need a sine 4 theta, so sine 4 theta here, and a sine 4 theta here, 4 theta. So I've got that sine 4 theta, that sine squared 4 theta taken care of. In my last 2 positions, I need those to multiply to be that 2. Well, the only way to multiply to be a 2 is 2 times 1. It doesn't matter where I put it in this particular example, so I'm going to put that plus 2 first and that plus 1 second. Now this is a product, so I can have either the first factor or the second factor equal to 0. Let's go ahead and set up those 2 cases. So I get that the sine of 4 theta plus 2 equals 0. Or I'm going to put a line here. The sine of 4 theta plus 1 is equal to 0. 2 really nice little mini equations to solve here. I'm going to subtract a 2 from both sides of that first factor, and I get that the sine of 4 theta is equal to a negative 2. Now, hopefully a big red flag goes off for you here, because sine can never be a negative 2. These are fractions on my unit circle, and sine can only be between, sine of any angle, including 4 theta, can only ever be between negative 1 and positive 1. So this is not possible, and we get no solution from this side. Time to go to that second factor. Now in the second factor, I'm going to start the same way. I'm going to move that 1 to the other side, and I get the sine of 4 theta is equal to negative 1. Now this is possible. So if I bring up my unit circle, I can think about where that y value, which is sine, where sine or y on the unit circle is equal to a negative 1. And that's going to happen right straight down here at 3 pi halves. This is the only place. So I can take that 3 pi halves and then add and subtract multiples of 2 pi. So this is going to give me the solution for 4 theta. So I have that 4 theta is equal to 3 pi halves plus 2 pi n. But I don't want 4 theta, I want theta. So I'm going to divide everybody by a 4. Divide by a 4. So this leaves me with theta is equal to, so I've got that 3 pi divided by 2 and divided by 4. So that's really divided by 8. So I've got a 3 pi eighths here. Plus, I can cancel the 2 and the 4, and I get pi halves n, and we've got our general solution. You are doing great, but be sure to watch this next one.